Welcome back everyone. In this video, we will be studying about the torsionally equivalent shaft with respect to a single rotor system. So far, we have studied the single rotor system in which a shaft of uniform diameter throughout its entire length is there, and at one of its ends, the rotor is being attached. But here, the shaft is in the form of a stepped one. That means at a different lengths, it is having different diameters. So in order to find the natural frequency, you are having the equation for finding the natural frequency omega, which is equal to square root of q divided by I, where I is the mass moment of inertia of the rotor which is attached at this end. But q is the torsional stiffness of the shaft. Since here you are having different length and different diameters for the shaft, that means you are having a stepped shaft. You have to convert this one into an equivalent shaft that is having the same effect, and that is known as torsionally equivalent shaft. And what is that same effect that we will be seeing now? Suppose here you are applying some torque at this rotor end. That means here you are applying some twisting by applying this torque. So this end will be having some deformation, angular deformation theta. If I am naming this end as A and the fixed end is O, then the angular deformation at the free end, that is theta of A, can be measured with respect to O. So that is theta of A with respect to O. That is the total angular deformation. And this angular deformation should be same in both this stepped shaft as well as torsionally equivalent shaft. That means the effect are same. So in such a way that we are converting this stepped shaft into a torsionally equivalent shaft. So if you are analyzing the left one, that is the stepped shaft, here different points based on this cross sections are there, A, B. So AB is shaft is having a length of L4 and diameter of D4. Similarly BC, CD and OD. So here you can, from this figure, you can find the theta of A with respect to O by theta of A with respect to B, and along with that adding theta of B with respect to C, and again theta of C with respect to D, and finally theta of D with respect to O. So this is the total angular deformation at the rotor end for the stepped shaft. And now you are converting this into a torsionally equivalent shaft where it is having a uniform diameter of DE, representing D equivalent, and a total length of LE, which is the equivalent length. So if such a shaft is there, or such a torsional equivalent shaft is there, then you are having the theta of A with respect to O. This is for the torsionally equivalent. So this torsionally equivalent shaft, angular deformation theta A with respect to O, and the one for this the stepped shaft, if I am calling this as equation 1 and this as the term equation 2, then the 1 and 2 should be same. So using this condition, we can find the dimensions. That means either the equivalent diameter DE or equivalent length of the torsionally equivalent shaft using this condition. So that we will be seeing now. Before that, I would like to mention the expression for this theta. That means you are having the basic torsion equation where tau by r, torsional shear stress by radius, equal to the remaining terms we need, that is the T divided by J equal to G theta divided by L. So if you are rearranging this one, you are having the expression for this angular deformation theta equal to TL divided by Gj. This equation we will be using for the analysis of this torsionally equivalent shaft. So theta equal to the applied torque into length of the shaft divided by the rigidity modulus G into polar moment of inertia J. So if you are considering the stepped shaft, here it is having different length. So this will be having some equation like T into AB is having a length of L4 and diameter of D4. So this will be like T into L4 divided by G into J4, because J is equal to pi d raised to 4 by 32. So this will be pi d4 raised to 4 divided by 32. Similarly, theta BC will be T into L3 divided by G into J3, which is pi d3 raised to 4 by 32. So you can relate these two equations, that means this main one along with this one, for finding the relation of this equivalent length or equivalent diameters. So here I can use this expression for relating this stepped and torsionally equivalent shaft. So I will be writing expression for each of these terms. So the left hand side theta AB plus theta BC plus theta CD plus theta DO will be becoming T into L4 divided by G into J4 plus T into L3 divided by G into J3 plus T into L2 divided by G into J2 plus T into L1 divided by G into J1, and this will be equal to the theta of A with respect to O for the torsionally equivalent. That means there is a single diameter and single length, so this will be equal to the same torque applied into equivalent length LE divided by G into J equivalent. And you are knowing that this J is equal to pi d raised to 4 by 32. That is the general expression. That means J is proportional to d raised to 4. If it is J4, it is d4 raised to 4, and if it is similarly d1, it is d1 raised to 4. So torque applied is same for all the parts of the shaft and the torsionally equivalent shaft, and G is the material property which is also same. So you can simplify this one, and finally we'll be getting the expression like the right hand side I will be writing first, that is LE divided by J. From that this will be DE raised to 4, and this is equal to L1 divided by D1 raised to 4 plus similarly L2 divided by D2 raised to 4 plus L3 divided by D3 raised to 4, and finally L4 divided by D4 raised to 4. So now we have related the torsionally equivalent shaft with respect to the stepped shaft. Suppose in question, if they are giving the D, usually we will be maintaining either of this diameter. That means either of the existing diameters can be chosen as the equivalent diameter. That means DE can be D1 or D2 or something like that. So if D is known, then you can find the equivalent length of the, that means the converted torsionally equivalent shaft length you can evaluate, that is LE. So from this one you can evaluate the torsional stiffness of the shaft QE using this equation GJ divided by L, that is GJE into LE. So if you are knowing this one, then you can find the natural frequency of the stepped shaft by converting it into torsionally equivalent shaft, and finally this omega n will be equal to QE divided by I of the rotor, that means the mass moment of inertia of the rotor. So this is the way how you can use the concept of torsionally equivalent shaft for solving such problem from the torsional vibrations. So this we have discussed for the single rotor system. In the next video we will be discussing the torsionally equivalent shaft concept for a two rotor system by solving a problem directly. Hope you understood, and thanks for watching.